Welcome to our advanced series on semiconductor physics. Today, we're tackling a fundamental concept in electronics and solid-state physics, the difference between intrinsic and extrinsic semiconductors, materials that are the cornerstone of modern electronics. This isn't just textbook knowledge. Whether you're designing integrated circuits, optimizing photovoltaic cells, or building quantum devices, semiconductors are at the heart of it all. Let's start with the basics and then dig deeper. What is a semiconductor? A semiconductor is a material whose electrical conductivity falls between that of a conductor like copper and an insulator like glass. What sets semiconductors apart is their controllable conductivity, which depends on 1. The crystalline structure of the material. 2. The energy band gap between the valence and conduction bands. 3. The presence of impurities, intentional or not. 4. Temperature, which affects the movement of charge carriers. These unique properties make semiconductors the core of diodes, transistors, LEDs, solar cells, and integrated circuits. Depending on the purity and behavior of the material, semiconductors are classified as 1. Intrinsic semiconductors. 2. Extrinsic semiconductors. Intrinsic semiconductors, the pure baseline. Intrinsic semiconductors, or I-type, are chemically pure materials. No dopants, no alterations, just atoms arranged in a perfect crystal lattice. The most common intrinsic semiconductors are silicon and germanium, both group 4 elements. Each atom forms 4 covalent bonds in a symmetrical tetrahedral arrangement. At this point, every electron is accounted for, tightly bound in a valence bond. There are no free charge carriers. Why intrinsic conductivity depends entirely on temperature. In intrinsic semiconductors materials, the number of charge carriers, electrons and holes, is determined solely by the material's properties and temperature. At absolute zero, intrinsic semiconductors act as perfect insulators. All the electrons remain tightly bound in covalent bonds, and the conduction band is completely vacant. But as temperature increases, things change. Thermal energy excites some electrons, giving them enough energy to overcome the band gap, the energy difference between the valence band and the conduction band. These excited electrons jump into the conduction band, becoming free to conduct electricity. At the same time, they leave behind holes in the valence band, positively charged vacancies that also act as mobile charge carriers. This process, electron-hole pair generation, is the only source of conductivity in an intrinsic semiconductor. Since the material is chemically pure, no donor or acceptor atoms exist to contribute carriers. It's thermal excitation, or optical excitation in some cases, or nothing. Why is this unique? Because there are no impurity atoms, thermal excitation is the only mechanism for generating free carriers. So in intrinsic semiconductors, conductivity is entirely temperature dependent and very limited at room temperature. At room temperature, intrinsic semiconductors 1. Exhibit a negative temperature coefficient of resistance, meaning conductivity increases with heat. 2. Maintain a perfect balance of electrons and holes. Each excitation generates one of each. 3. Show low but non-zero conductivity, which grows exponentially as temperature rises. This behavior is described quantitatively by the equation, where N is the number of free electrons, P is the number of holes, and N subscript I is the intrinsic carrier concentration. Under thermal equilibrium, generation and recombination rates are equal, so the concentrations of electrons and holes remain stable and equal. The temperature dependence of carrier concentration. The intrinsic carrier concentration is not static. It depends strongly on temperature and band gap energy as shown in the equation on the screen. For example, in silicon at room temperature is shown. This value is orders of magnitude lower than what's achievable through doping, and explains why intrinsic semiconductors have poor conductivity unless operating at elevated temperatures. So, what are the key properties of an intrinsic semiconductor? Let's break it down. First off, it's made from completely pure material, no doping, no impurities. 2. It has a perfect balance of charge carriers, equal numbers of electrons and holes created by thermal energy. 3. At room temperature, it's a poor conductor, but not useless. 4. As the temperature rises, conductivity increases fast, and I mean exponentially fast. And finally, the Fermi level, that key reference point for energy states, sits right in the middle of the band gap, reflecting that perfect symmetry. We dive into extrinsic semiconductors, which are engineered for performance. To enhance conductivity and control carrier type, we introduce impurities into intrinsic materials. This is called doping. Doping transforms a weak, balanced conductor into a highly functional material. The result, extrinsic semiconductors, which come in two types, N-type and P-type. 1. N-type semiconductors, electron-rich. Doping silicon or germanium with pentavalent atoms, such as phosphorus, arsenic, or antimony, introduces free electrons. These dopants have 5 valence electrons. 1. 4 form covalent bonds with silicon atoms. 2. The 5th is excess and becomes a free electron. This increases the number of negative charge carriers, hence the term N-type. So, what are the key characteristics of an N-type semiconductors? Let's break it down. 1. Electrons take the lead. They're the majority carriers here. 2. Holes, still present, but they play a minor role. 3. The Fermi level shifts upward, moving closer to the conduction band, making it easier for electrons to move. And here's the kicker. It's highly conductive, even at room temperature. 2. P-type semiconductors, hole-rich. In P-type semiconductors, the material is doped with trivalent elements like boron, B, aluminum, or gallium, all with 3 valence electrons. These atoms, 1. Form 3 bonds with silicon. 2. Leave 1 bond incomplete, creating a hole. These holes act as positive charge carriers, dramatically improving conductivity. So, what are the key characteristics? Let's break it down. 1. Holes are the majority carriers. They do most of the conducting. 2. Electrons are still around, but they're the minority. 3. The Fermi level drops down, moving closer to the valence band. 4. And as you increase temperature or doping, the conductivity gets even better. Energy band and Fermi level shifts. The band structure doesn't change with doping, but carrier concentration and Fermi level position do. 1. For intrinsic, the Fermi level is centered in the band gap. 2. For N-type, the Fermi level shifts upward toward conduction band. 3. For P-type, the Fermi level shifts downward toward valence band. This shift directly impacts how easily electrons or holes can move, enhancing the material's electrical behavior. Applications and real-world relevance. This isn't abstract. This is the backbone of modern electronics. Intrinsic semiconductors are used in 1. High-purity photodetectors. 2. Optical and X-ray sensors. 3. Scientific instruments. While extrinsic semiconductors form 1. Diodes, p-n junctions. 2. Transistors. 3. Solar cells and LEDs. 4. Digital ICs and microprocessors. Mastering these materials is what powers smartphones, satellites, AI systems, and sustainable energy technologies. In summary, 1. Intrinsic semiconductors are pure and conduct only through temperature-induced carrier generation. Their conductivity is modest, but predictable. 2. Extrinsic semiconductors are tailored through doping to dramatically boost conductivity and define carrier type, enabling nearly every modern electronic device. The key difference: precision control. If this deep dive clarified how semiconductors work, give the video a thumbs up, subscribe for more advanced electronics content, and drop your questions in the comments. Want a follow-up episode on p-n junction physics, MOSFET operation, or semiconductor equations? Let us know. Until next time, stay curious, stay sharp.